Okay, in this second part of 2.2, we're going to focus specifically on normal calculation. So what we've done with density curves, we've talked about the fact that underneath the density curve we have an area of 1, and when it is normal, the median and the mean would be the same. When it's skewed, we talk about that kind of thing where the mean and the median are apart from one another because of the skewing, and we've also talked about normal distributions and how the 68, 95, 99.7 rule allows you to estimate where z-scores are, or percentiles are, based on what we know. I'm going to focus in this section on the normal calculations using the tools of Table A and your calculators. This is a reminder of what we do every time we're dealing with or exploring quantitative data. We always make a graphical representation and then communicate the overall pattern, center, shape, spread, all that stuff, and outliers. This particular section we're dealing with has us look at the idea that this overall pattern and the lack of outliers and the fact that it is largely symmetrical and unimodal, we can think of it as a normal curve. Once we've done that, then the numerical summaries that we're going to deal with allow us to then look at talking about the mean and our standard deviations above and our standard deviations below. This is a special kind of density curve. Remember, density curves have exactly area of 1 underneath, and our normal curves will have 50% below and 50% above. So every time I want you to get in the habit to just slow down and figure out what it is you're being asked to use. And so here you're just asked to find the proportion of the observations given a z of 0.081. So remember, z's tells you how far you are away, how many standard deviations you are away from 0. So in this case, a z of 0.081 is right there. And then the proportions, the percentiles, the area, these are asking the same question, and it always talks about the area below or the percentile or the probability that it's at that cut point or below. And we know enough about the normal curve to recognize that we've got 50% of the area right there, and then a little less than the 34 that goes right there. So 58, about 80% should be what we get when we use the accurate tool. So to use the tool, we have a 0.81. So the 0.8 we're going to find here, and the 0.01 we're going to find there, and then we're going to read into the middle to find that it's 0.7910, which we can read that as about 79% of the time. Or the area underneath that curve is 0.7910, or the percentile is at 79 percentile. All of those are using the same tools to answer a question that's just phrased differently or looking for a slightly different representation of this piece right there. This is just a reminder of what I just said, so go ahead and read this and write down what you need to do, but remind yourself how to read the z-score, and that also that the 4-digit decimals can be interpreted in a bunch of different ways, but they mean the same thing. So go ahead and read that and write down what you want. Pause it if you'd like. I'm just going to move on. Once you've looked at a set of data and you've decided that it can be described or interpreted as a normal distribution, and so we're going to take the individual data points and just treat it as if it were normal, we need to communicate that, and then we need to start building our representation of that. Instead of graphing the actual data, we're going to graph the data as if it were normal, which means we're going to, step one, we're always going to state that it's normal, and we can do that with just a big old N, and we're going to communicate the numbers of interest, which will be your mean, your mu, and your standard deviation, which is a sigma, not a theta, because I said it a million times wrong in the last one. So you're going to describe this particular one with those, you're going to define it. Then we're going to perform any calculations that it asks us to perform, whether we use a table or whether you use a calculator, you're going to communicate very clearly what you're doing as you're doing it, and then you're going to actually answer the question in the context of the problem. So if we're going to use the table of values to find the area below or the percentile of that cut mark or the probability that something is at or below that mark, we can go ahead and use a table of values. Remember though, whenever you're doing a problem where you're being asked to deal with a distribution that is approximately normal, you're going to want to start by making your sketch here, right? And you're going to, in this case, the percent of students score below 80, you're going to have to start by finding the z-score, or later we're going to talk about ways to doing it with the calculator. But the z-score is going to be your cut point. In this case, it's 80. The mu, or the mean, it's a mu because it is we have taken the actual data and we're moving it to a normalized curve, so that our mu is going to be 76.4 and our standard deviation is 7.9. When we do that calculation, we end up with a number that looks like that, so we're going to go ahead and round it so we can look for it in the table. So the standard deviation is 0.46. So we can then look at what we know so far. So here is a standard deviation of 0 and here's 1. So 0.46 is going to be somewhere there. We can use our approximations. We've got 50% plus another maybe half of that 34, so maybe 50, 67, maybe a little less than that. And so you can go ahead and get a sense of about how much it's going to be before you even start using the table. So we're going to go ahead and take the table. We've got the 0.04. We're going to look here, and it's right there. 0.04. It didn't look like, anyway. And then the 06 is right there, and then you're going to go right into the middle, and there is our amount. So the area below 80 is 0.6772. So we're going to answer the question, what percent of the students scored below your score of 80? It's about 68% scored below 80. And if we were found what percent scored above you, all you would have to do is subtract 1 minus. And so you would get 60 100 minus 68, which for some reason right now is really hard. That's 32% scored above. Anyway. So just so we're about to move to calculator commands, but I want to make sure that we understand where those commands are coming from. You won't be asked to explain where they're coming from, but I want you to understand that what we've been looking at consistently is the probability density function. That's what that PDF stands for in this case, not the PDF like we're used to in computer land. But the normal PDF, we know now, for example, that there's 50% from a bunch of negative standard deviations away all the way up to no standard deviations away, and then from 0 to 1 positive we have about 34% more data, and then from 1 to 2 we have about 13.5% more data. That is the way it rolls. Now we're going to look at it in another way, which is the cumulative density function. That's where that CDF comes from that we're about to look at in our calculator commands. So the normal CDF is a cumulative representation of the exact same thing. So from -4 to 0 standard deviations away from the mean, we have 50% of the data. And then when we add that next layer of 1 standard deviation, we get another 34%. And so cumulatively here we're at 84. And then when we add that other 35%, we're at 97.5%. And then we're going to add a little more until we get all the way to 100. So cumulative density function, we're going to be using the normal CDF command a lot. And this is where it comes from, the cumulative density function. So if we decide instead of using the table, we're going to use a calculator, the calculator functions once again are going to focus on normal CDF and the inverse of normal CDF. The second vars, we're going to turn on the, we're going to turn on the calculator, and then we're going to hit second VARS, and right above the IRS you'll notice it's DISTR or something like that, distribution, because we're dealing with a distribution where something is in the distribution of the data. So always, 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 here's our information. We're going to go ahead and take that information and sketch it out, and in this particular case I've sketched it out, and I have the question 9 or fewer batters. So here would be where 9 or fewer batters on. You've estimated it's 50, maybe 60. Then you can go ahead and make sense of it and then go ahead and use the calculator to help you out. And with a calculator, this is what we're going to be looking at. Turn on, second vars, normal CDF. We have to, when we're using the calculator, you're going to write these words on your paper, and then directly underneath them you're going to go ahead and write the numbers that are appropriate for this problem. So you're going to write the words normal CDF, and my pen doesn't work very well. So the lower bound in this case, it's going to be way back here, which we can put any really low number, like negative, should be like negative infinity, but we don't have access to that button on that. The upper bound is that 9 that we're looking for. The mean is 8.2, and the standard deviation is 2.8, and then once you put that in the calculator, it's going to give you 0.61 something something something. So it's about approximately 61% of the time he struck out a batter 9 or fewer times. When we repeat this situation with the, we've already done this one with the table over here. I don't need to sketch it again. We know it's going to be about 35, 33, 34, depending on what we saw. But we're going to go ahead and write down the words normal CDF, lower, upper, mean, standard deviation, and we're going to go ahead and put our numbers on paper as well as plug them in the calculator. So you're going to go ahead, and our lower bound in this case is going to be the 80 because we're looking for above. And then the upper bound would be positive infinity, but we don't have that ability, so just slap some big number in there. And then the mean would be 76.4, and 7.9 would be your standard deviation. Once you plug that in, remember it's normal CDF, then it gives you about a 0.32, about 32% of the time the student scored above your score. We're going to use the opposite of normal CDF, which is inverse norm. So the information that you're going to need there is the same thing. We have to define the particular normal curve we're talking about, in this case having to do with Tin-Lincecum, and then instead of needing the upper and lower bound, we're going to get that number that's in the table, the percentile, the area below the curve, that kind of stuff. So the number of strikeouts in the 90th percentile, we would turn on our calculator, we would hit second vars, once again getting us to the distribution part of the computer. Then we would hit you write this stuff down, those words, and then underneath it you would write down inverse norm. The percentile we're looking for has to be in decimal form, and then you're going to go ahead and put the 8.2 and the 2.8 into the calculator, and then it'll go ahead and tell you what the number of strikeouts it is. So when you put in inverse norm, you would put the 90% as 0.90, and then the mean, and then the standard deviation. Remember, label whatever calculator commands in the actual words as well as in the number, and then make sure you have your sketch. And then here we're going to get this number out of the calculator, answer the question. So the question is what number of strikeouts is in the 90th percentile, and you would say 11.78, or approximately 12 strikeouts would be in the 90th percentile.